Okay, so in this recording, we're going to look at some examples of percent ionization, dissociation coefficient alpha, the relationship between alpha and Ka, and just some theory about something called Oswald dilution. I'm going to have to go through some theory first here briefly. It doesn't really belong much anywhere in a particular place in the course, but it does reflect some things here for problem solving. The problem solving that we're going to be looking at is number 6, number 16, number 17, number 15, and number 30. Okay, those are the questions that will involve this this recording. Okay, before that, I'm going to just briefly remind you about percent ionization. You already know that the percent ionization is how much does the acid actually ionize, okay, in percentage. So if I have my weak acid with a concentration C initially, and then it reacts minus X, and then X amount of A, then the amount ionized would be X moles. That's the amount ionized. Now, if I want it in percent ionized, I would take the X divided by actually the initial concentration, how much I started off with, times 100. Okay, that's the percent ionization. So X is just A minus, and the reason we didn't put H3O plus because there might be contribution, let's say, of water or something else, but A minus always just comes from the amount ionized divided by the concentration of HA, actually initially, and most of the time initially is equal to the concentration left over in solution, depending on the alpha. Now, the dissociation coefficient, the coefficient before having the percent, is the X divided by the initial concentration. And we can go through a calculation to actually prove to ourselves that indeed, as I become more dilute, as the concentration decreases, the amount ionized may increase, but the percent ionization decreases. And I'm not going to actually go into detail here, but if, for example, I take 1 molar acetic acid, okay, if you remember through the derivation, remember for any acetic acid or any weak acid, Ka is X squared divided by HA minus X, and if X is negligible, I could remove it, and you solve for the X, which is simply your H plus, which is also equal to the A minus. So if I want the X, or the amount ionized, it's going to be the square root of Ka times HA. And that's very easy. So X is the square root of Ka times HA, concentration. So it's directly related to the concentration. So if I calculate for 1 molar, with acetic acid, the Ka is 1.8 times 10 to the minus 5. For 1 molar, take the square root of that multiplication, you get a number. And if I ask for the percent, it's this number, which is the X, divided by 1 times 100, I get 0.42%. Now, if I dilute this acid 100 times, so it's divided by 100, and so my new concentration of acid is 0.01. Well, very simply, again, X, or A minus, is the square root of Ka times 0.01 now, because now it's a new concentration. I get the X. Now, if you compare this X to the one before, indeed, before the X, the amount of moles is greater than when it's diluted. But look at the percent ionization. I take this divided by 0.01 now. Now look, I'm dividing by a much smaller number. The percent ionization actually increases. Okay? And so dilution increases the percent ionization. Okay, so as I become more dilute, the percent of ionization increases. All right, so that's it for percent ionization. And this is the graph that actually, shows me that. And I do want you to keep this graph in mind. This is the percent ionization, and this is my initial concentration increasing of the acid. And look at it backwards. As my concentration decreases, and as I dilute, look at the percent ionization. It skyrockets. It goes so high to the point that this weak acid may eventually actually almost reach 100% ionization. So at extreme dilution, my acid becomes almost 100% ionized, which almost looks like a strong acid, though this is a weak acid. And which gets me to the next point, dissociation coefficient alpha. Well, already we know that alpha is X divided by initial concentration. So it's N moles dissociated divided by the N moles initial, which is X divided by C, or concentration dissociated divided by concentration initial. Okay, we're going to derive alpha now in terms of K. Now, if you remember, we've seen some things like this before. So at time equals 0, my initial concentration of my acid is simply C, and the products, the conjugate base of that acid is 0, and H3O plus is 0. And at equilibrium, this would be C minus X, X, and X. Now, if I convert this to something in terms of alpha, so instead of X, remember if you go here, X alpha equals X times C, so what is X? X is simply alpha C. And so if you substitute this X becomes alpha C for C alpha, this X is C alpha, and this here, C minus X, C minus C alpha, and factor out the C, so this becomes 1 minus alpha. So you're all fine and dandy with that, and we're done. And we continue. Now, what is the K at equilibrium? K of this reaction is products divided by reactants. So let's just put the products. It's the acetate, there we go. H3O plus, there it is, products divided by reactants, acetic acid divided by water. Great. Now, usually you're like, water? I thought water is equal to, we don't include it. Well, actually, water has a concentration, don't forget, it's 55.5 molar, but I multiply by the C of the reaction, and I get Ka. Okay, so again, that's the Ka expression. So you already know how to get this Ka, and then you're fine with that. You don't include the water in it. Now, this Ka is simply, if I go back, you already know that it's also x squared divided by C0 minus x. You're all experts at this equation now. But if I want to calculate it in terms of alpha, this is going to be the acetate is C alpha, the water is C alpha. divided by the acetic acid is C into 1 minus alpha. And clear. Now the Ka becomes, if you look at it, this C simply cancels. One of them cancels, so this becomes C alpha squared divided by 1 minus alpha. Now this equation can come into handy sometimes. If I want to just relate the dissociation coefficient to the concentration or to the Ka, I can have this relationship, and it can simplify some reactions, as we're going to see in the problem set. Now, I'm not going to get into details here, but there's a dilution law, and this is called Oswald law of dilution. And Oswald literally said that as I dilute, so as C decreases a lot, then alpha starts to increase, and it increases to the point that it tends to 1. And if alpha tends to 1, remember, alpha is x divided by c, and if this alpha is 1, that means my x is almost going to be c, and if x is c, that means I'm almost like a strong acid. This acid completely dissociates. And so weak acids, and you already know that because of this graph that I just showed you, that as I dilute greatly, my weak acid will start to dissociate to the point that the dissociation goes to completion. Of course, there's a limit to this, and does the acid always dissociate? There's a derivation for you. I'm not going to go through it. It's in your textbook. And if you want, all that it's really saying, it's putting alpha in terms of K, and we're putting water with a H3O plus at a concentration 10 to the minus 7. And what it's saying is, as I infinitely dilute the system, okay, at infinite dilution, that means that my HA really concentration is negligible relative to pure water, right? Only water exists at this point, at infinite dilution. And therefore, my H3O plus will be mainly coming from water, which you remember that's 10 to the minus 7. Great, so now that you know that, and we already discussed that, which is great, now you substitute this 10 to the minus 7 into the calculation of Ka. So instead of H3O plus being the same, C alpha, you substitute for H3O plus, put 10 to the minus 7. Net result, okay, I get alpha in terms of Ka at infinite dilution. And all I really want you to take is a take-home message is the following. That if the Ka is greater than a big number, greater than 10 to the minus 7, if this guy is much greater than 10 to the minus 7, or at least 10 times, then this 10 to the minus 7 is negligible. That means what happens? This becomes Ka divided by Ka, then the alpha is almost 1. So alpha tends to 1 at infinity of dilution. That's all I really want you to take. And that if Ka actually is very small of that acid, if that Ka is very small for the acid, less than 10 to the minus 7, even if I throw that acid in the beach or in the sea, you know what? It's not gonna dissociate. Alpha tends to 0, because no matter what happens, this Ka is way too small, and it's still gonna be a weak electrolyte at infinity dilution, and you're not going to dissociate it much. Okay, so alpha tends to 1 at infinite dilution. Great. Now that we're done with the theory part, Let's start jump into the questions. Though you could have solved these questions without this theory, of course, or else I would not have assigned it. But I just want to make sure that it's all covered because it sometimes can help with certain calculations. The pH of a couple acetic acid is 4.8. For 0.1 acetic acid solution in water, we can say, this is number 6, that the acid completely dissociates into its conjugate base. Guys, this is a weak acid. They gave you Ka, so idea of completely dissociates is simply never the case. Okay? Weak acids only partially dissociate. I mean, it does not completely ever dissociate, or else it would be called a strong acid. So this is definitely wrong. Dilution favors dissociation. Well, after what I just talked to you about, and your mind should be, okay, here's my graph. Dilution, here, as I dilute, this is concentration, this is percent ionization. Dilution does favor dissociation. So you're all fine with that. If we dissolve 0.1 molar of acetic acid in 1 liter, so that's giving me the 0.1 molar, at equilibrium, half the acid is dissociated. So literally they're asking, what is the X? How much dissociates? That we actually need a calculation to see if half of it will dissociate. The acetate ion is a strong base. Well, this is a weak acid. Acetic acid is a weak acid, so its base is a weak base. So it cannot be strong. Weak gives weak. Okay, so this is incorrect. And the pH of the solution is equal to 4.8. Well, we actually have to do a calculation here, but just, a quick one. If I look at my concentration, 0.1, clearly that concentration is greater than 100 Ka, because this is my Ka. My Ka is 10 to the minus 4.8. Multiply it by 2, so that's like plus 2 here. And definitely this 0.1 is still bigger than this number, okay? So you could do that in your mind, and therefore I could easily get pH. Now, if you really have to, you could do the calculation, but I just want to show you something for a moment. The pKa is 4.8. If you look at this equation, if this guy is 4.8, no matter what my concentration is, dilute, concentrated, no matter what it is, this pH can never be really bigger than the 4.8, okay? Unless this guy is very, very dilute. And it's not, it's 0.1 molar. Or simply substitute in, instead of K, but just put 0.1, pKa is 4.8, and get a pH. It's definitely, the pH of the solution is not 4.8, okay, if you have to do a calculation. All right, so now, like I said, I have this as being correct for sure. And let's do the percent, how much is going to get ionized, okay? And so how much is going to get ionized? Well, you have an acetic acid, and remember this is C minus X, and in terms of alpha, if I want to. And so the amount ionized, and we just discussed this, is simply X, right? X is going to be the square root of Ka times C. And yes, it can come in very handy, this equation. Square root of Ka times C. So Ka is simply 10 to the minus pKa. Kc happens to be 0.1. And there you go, that's your X. Of course, this is only reasonable if C, the concentration, or C0 is greater than 100 Ka, and it is. So look at this X. Is this amount half of 0.1? No, it's not. It's much less than half of 0.1. So actually, the answer is incorrect. Now, you could also calculate alpha if you want to, but there is really no need for alpha. But just as a reminder that as C decreases, alpha increases, or the percent, the dissociation or the dissociation constant increasing. And so dilution favors dissociation is indeed a correct answer. And that's our graph. The only answer for number 6 is B. Calculate the dissociation constant Ka of a weak acid. The ionization percent is 1.6. Now, if there's here in your book, it wrote 60, so there's a mistake in the textbook. So watch out. The percent ionization is 1.6. Alpha is 0.016. In a solution, concentration of the solution is 0.0952. What do they want? They want Ka. Oh boy, this is the first time that they ask for Ka. Well, actually, it's not so bad because I already know that for a weak acid, what is the Ka? Right? What's the Ka for a weak acid, guys? Ka is simply x squared divided by C0 minus x. If you want, you could also get it Ka in terms of alpha, which we just derived today. Now, they gave me the alpha, 0.16. Well, we're not really used to reacting with alpha, so I could easily get my x, right? Alpha equals x divided by C, so my x is alpha times the concentration. We have alpha, we have the concentration, that's my alpha, that's my concentration, so alpha C is equal to x. Let me grab my x. Once I have my x, which is the amount dissociated, I simply substitute that x into my Ka expression, and which is x squared divided by C0 minus x, and we're done. Okay? And you're all happy that that is exact. And usually, guys, with Kas, it's best to use this because Ka, some of you might ask, shouldn't I ignore x, or can I remove x from the denominator? If I'm doing a calculation for Ka, it's best that you keep the x in, okay? At least my opinion. Now, some people tend to disagree with that, but in my opinion, even if x, is a small number, substitute it in because you have the number. It's not like I'm really simplifying the equation anything. Ka is whatever this x number is, so 1.52 times 10 to the minus 3 squared. C0 is 0.095 minus this x, 1.52 times 10 to the minus 3. Now, does this number, is it negligible relative to the initial? It might be, but then the calculator does it for you. You don't have to worry, right? And actually it is. It happens to be, so I could have ignored x, but, I still prefer to keep it at least with the calculation of Ka. So get the Ka value, and you could have also gotten the Ka from alpha. This is just as a pointer. Again, Ka in terms of alpha is concentration alpha squared divided by 1 minus alpha. And since you have the alpha amount and you have the initial concentration, you can get K. And in this sense, they also, they did no negligibility here. They didn't neglect anything in the derivation of K. And so simple substitution, and you should get the same answer, and indeed the answer is the same, and the answer is E. Number 17. An acid HA is placed in water solution with the molar concentration of the solute is 10 to the minus 3. Now they're saying HA dissociates in water according to the following equation. I don't even know why they bothered to put that sentence. If it's a weak acid, خلاص. There's no need to tell me what the equation is. We measure the pH of the obtained solution to be 3.7. Okay? So you're given the pH. The degree of dissociation is, in other words, alpha. When they ask you for the degree of dissociation, it's alpha or the percent ionization. If it's a ratio, you would see ratios here. And here it's in percent dissociation. Well, this is how I did it initially, and then of course I could do it in another way. If I have a pH, guys, what does that mean? It means I could easily get the H3O+, which is 10 to the minus pH. And why do I want to do that? Because once I have the H3O+, well, I have X, the dissociated amount, right? And this X is simply C0 alpha, so I could also get alpha if I want to, okay? So X is, this is H3O+, C0, and alpha. I have C0, I have the H3O+, so I could get alpha. Okay, now let's see. And of course, once you get alpha, you notice that alpha is 0.19, and the percent then ionization is times 100, which is 20%. Now, the way I'm more used to it is percent ionization is X, not in terms of that, so X divided by initial concentration. So what is my X? 10 to the minus 3.7 divided by my initial concentration, which is 10 to the minus 3 times 100. And guess what? You get the same answer, 20%. Number 15, I'm going to keep on its own.